Hello, and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends at Linode. With their new managed database service, you can launch a production-ready MySQL, Postgres, or MongoDB cluster in minutes, with automated backups, 40 gigabit connections from your application hosts, and high-throughput SSDs. Go to dataengineeringpodcast.com/Linode today and get a $100 credit to launch a database, create a Kubernetes cluster, or take advantage of all of their other services. And don't forget to thank them for their continued support of this show. Data stacks are becoming more and more complex. This brings infinite possibilities for data pipelines to break and a host of other issues, severely deteriorating the quality of the data and causing teams to lose trust. Siffle solves this problem by acting as an overseeing layer to the data stack, observing data and ensuring it's reliable from ingestion all the way to consumption. Whether the data is in transit or at rest, Siffle can detect data quality anomalies, assess business impact, identify the root cause, and alert data teams on their preferred channels. All thanks to over 50 quality checks, extensive column-level lineage, and over 20 connectors across the data stack. In addition, data discovery is made easy through Siffle's information-rich data catalog with a powerful search engine and real-time health status. Listeners of the podcast will get $2,000 to use as platform credits when signing up to use Siffle. Siffle also offers a 2-week free trial. Find out more at dataengineeringpodcast.com/Siffle today. That's SIFFLET. Your host is Tobias Macy, and today I'm interviewing Frank Liu about the open source vector database Milvus and how it simplifies the work of supporting ML teams. So Frank, can you start by introducing yourself?
Thanks for having me on the show today, Tobias. So my name is Frank. I'm currently a director of operations at a startup called Zilliz. We do vector databases. I've been sort of in and around ML for quite a while. After graduating, I worked on the computer vision and machine learning. We're sort of like a hybrid research software development team over at Yahoo. I had my own company for a while. We were doing machine learning for IoT platforms. And now I am at Zilliz, where we do sort of ML infrastructure.
And do you remember how you first got started working in data?
That's a great question. And I want to say, back 6 or 7 years ago at Yahoo, I think that's when I really was able to see what big data means. And they had quite a large amount over there. Big data, I think, back then was more of a catch-all term. Some folks considered it, if I have a data set, maybe 1 million examples or 1 million samples, that would be big data. To other folks, it might have been 10 million. But to Yahoo, we had, billions of images, everything you can think of. I think a big challenge there for the team that I was on in particular is that we needed to figure out how all of those fit into these different models, how all those pieces of data could be used to sort of improve a lot of business functions. And I think a lot of that really spills over into what we're doing today with vector databases as well.
So in terms of that, can you describe a bit about what the Milvus project is and some of the story behind how it came to be and why you decided that this was the area that you wanted to spend your time and energy?
Milvus, I want to say it was created at Zilliz probably about in 2018, and it was open sourced, I think, in October of 2018 as well. And the idea behind there is that we had so many users come to us, we had so many potential customers come to us and say, look, we realize you're doing a data storage platform, but we need something to be able to store, index, and search across massive quantities of data. I think embedding data, so vector data. One of our very first users came to us and said, we have 50 million of these vectors. This was 4 years ago, so they already had quite a bit of data that they wanted to search and index already. And this is what really prompted us to get started on Milvus, get started on this vector database. We did end up open sourcing it later. Milvus is actually now a part of the LF Linux Foundation for AI and Data. And I'm going to talk a little bit about sort of what a vector database is and how it works as well, sort of as a follow-up to this question. The idea behind a vector database is that it's meant to store what we call unstructured data. You see, I want to say, ever since there's so many of these really, really popular SQL databases out there, MySQL, PostgreSQL, some of these very distributed ones as well, CockroachDB, so on and so forth. And all of these are meant to store in some way, shape, or form either tabular or other structured / semi-structured data. Objects, JSON documents, if you're using MongoDB, Redis is a key value store. But so much of data out there today, right, is unstructured. And by unstructured, we're looking at images, For example, you can have images of a variety of different sizes, a variety of different resolutions. Audio, they could be different audio snippets spoken by different people, music, images, audio, video, text. All of these are what we consider unstructured data. And there's so much of it out there today, right? A good statistic that I like to quote is that I think something like 720,000 hours of YouTube videos are uploaded per day. And we want to have a way to search across all of these videos from a semantic perspective. Right? We want to be able to search across all of them, not just by, let's say, the title of the video, or in the context of YouTube or any other video sharing platform, not just the title of the video or the description of the video, but also the contents of the videos themselves. We also want to be able to use these pieces of unstructured data. That's really where the idea behind the vector database was born. And I want to say within the first year or 2 years, we ended up communicating in some way, shape, or form with over 1,000 enterprise users of this open source project, which we saw tremendous growth internally at Zilliz. And yeah, it's been a ride ever since.
Digging a bit more into this idea of the vector database, there's another conversation I had a little while ago with the folks from the Pinecone project. And there's I know it's not the same space, but at surface value, what could be viewed as a similar concept of the bitmap database that the folks at Pelosa project builds, where it's actually a database that just stores the indices on the underlying data so that you can do faster querying across these different data sets. And I'm wondering if you can just talk to some of the types of use cases that a vector database enables and how it might compare to or contrast with this idea of a bitmap database. And given that these are sort of unique types of database engines compared to the systems that you mentioned that people are familiar with in the MySQL, Postgres, Cockroach, document databases.
I want to say that the use cases for vector databases, I think most people today would associate them with, you have an upstream machine learning model and you want to be able to, store, index, and search these embedding vectors from those machine learning models, right? But there are plenty of other examples out there of folks turning pieces of unstructured data into vectors or into embeddings using these, what I like to call handcrafted algorithms. So I'll go over some of the ones, sort of both sides as well, that use these machine learning models, as well as ones that use more handcrafted features. The idea here is that I'm going to go back to the example of video, right? Let's say I am a short video platform and I want to be able to understand user behavior. I want to be able to recommend new videos. If you look at TikTok and some of the other sort of pretty popular short video platforms out there, I think a lot of folks would say that they do a pretty good job of doing recommendations. There's quite a bit of semantic information from inside the video that we can look at as well. And a common use case that we see here in the Milvus community is taking the video, indexing either the entire video or individual frames of the video, and being able to recommend new videos based off of that. Or let's say being able to serve ads based on the contents of the video that I like to watch. That's one of many use cases when it comes to video. Another one that I enjoy talking about with other folks is security. So there's I'm not sure how common it is, but Trend Micro at some point came to us and said, you guys are doing great work. We want to be able to do threat analysis over these APKs, over Android APKs. So we have an existing pool of APKs that we know is malware. We've taken them, we've analyzed them, and we want to be able to understand if a new APK comes on, if new APK comes online, we want to be able to index that and see if that's malware as well. And with the number of apps that are out there today and just growing, they had the system into production. They had quite a large number of APKs and other applications that they were scanning, right? I think this is a great example of an application that doesn't necessarily use machine learning upstream. And what they did was they took the contents of the APK itself. So they looked at, let's say, I don't know all the details, but the number of reads and writes to disk, or how often it accesses the network. They turned all of these features and they put all of them together into an embedding, I think very much in the traditional machine learning sense. And they use that, to great effect within Milvus, right? So these are just two of the many examples. And I really highlighted these two because you see in the video case, if you want to do recommendation or if you want to serve ads, there's these machine learning models that sit upstream. But when it comes to, let's say, threat detection, something that we did with Trend Micro, there's a lot of other features that you can use as a part of the embedding as well. And I'm also just going to list off some of the other use cases that we see these days with vector databases. We see intelligent chatbots. That's actually quite a common one for a lot of our user base. There is reverse image search. We did a very, very, Cleveland Museum of Art. They also did one of my favorite applications where they got a reverse image search application up and running in, I want to say, just under a week with a very, very tiny team. So I thought that was very impressive. There's semantic text search. So if I want to be able to search over text, not just by keywords, but also, let's say, by the contents of the text or the contents of the phrases themselves. And there's many, many more out there as well. As I mentioned, I think we've onboarded at this point, well, I wouldn't say onboarded, but we've communicated with in some way, shape, or form over 1,000 enterprise users. The second part of your question earlier, talking about these other different types of databases, there are bitmap databases. You have your traditional, we were mentioning Cockroach, Postgre. There are these traditional relational databases. And what I will say is that a common question that I get, I think a common misconception when I speak to a lot of folks, when I talk to a lot of folks about vector databases, about our architecture, and even I would say when I talk to folks in the Milvus community and internally as well, is that Milvus one day is going to replace MySQL, or replace PostgreSQL, or replace MongoDB or whatever. And that's absolutely not the case. We don't see Milvus as replacing all of these traditional relational or traditional object databases, wide column stores, so on and so forth. But I think sort of my vision for vector databases is that they're used in conjunction with these traditional databases, Mongo, Redis, etc., to build, to open up new revenue streams if you're a company, or to help you understand the massive quantities of unstructured data that you have as well. Milvus is not meant to be like the next evolution of a single database that you would ever want to use. That's not the case, right? And I think down the road, there will be more and more, let's say in the next 3 to 5 years, you will see more and more of these applications that use both of these different types of databases for unstructured data and databases for structured data, use them in conjunction, use them to great effect.
In terms of the similarity search capabilities, one of the things you mentioned is being able to generate these embeddings of video files and then determine whether or not there are similarities between different videos, or the reverse image search use case. And I can imagine it being used in a copyright enforcement use case where you can say, I want to detect whether or not there is some portion of this song used in this video. And I'm wondering if you can talk to some of the applications of being able to do kind of subset matching, where you say, I have these two distinct vector embeddings. I just want to know whether or not there is some common portion of these vectors. And so I can use that to determine whether or not these two videos are using the same scene in the middle of the video, but the rest of the video is completely disparate.
Deduplication, both audio and video deduplication, is a big part of our user cases as well. And you were talking about specifically how, let's say I have like a subset of the vectors that I want to look at, or a particular, let's say I have a 1024 dimensional vector and I only want to look at the first 100 elements, right? And this also sort of ties in with the idea that a vector database is very, very different from a traditional relational database or an object database or any other database for semi-structured data. And when it comes to vectors, you really are looking mostly at two things, I would say. The distance between different vectors that correspond to obviously different pieces of unstructured data. Let's say I have two images and there are two vectors there. So you look mainly at the distance between those two. And then the other thing that you might want to look at is sort of vector arithmetic, I like to call it. So I'll talk into both of these in a little bit further detail. The first, I think, is when you look at the distance between two vectors, you're looking at them as a whole. So I was at SIGMOD, I want to say, which is an academic database conference. I want to say about 2 months ago. And, I was talking to a lot of folks, and a lot of the questions that I got were, why can't I store these vectors in a tabular database, in a relational database, and have each column be an element of the vector? Right? So I have, let's say, 1,000,000 images, and I have these 1,000,000 images correspond to 1,000,000 vectors that come from these machine learning models, that are generated from these machine learning models. And I think there's a lot of misunderstanding there about what the vectors are there to represent. I can absolutely do that, right? So I can absolutely store vectors in a relational or a table-based format, but each column of the vector is, it's not very, very meaningful. Right. And what's more meaningful is the distance between them. So for folks who are a little bit more maybe sort of ML or sort of data science savvy, if I have these high dimensional vectors that come from these machine learning models or high dimensional tensors, and let's say I have 1,000,000 of them, if I were to multiply all 1,000,000 by the same sort of n-dimensional or high-dimensional rotation matrix, the resulting sort of embedding space that I get is actually exactly the same as it was before. It is an entirely valid embedding space. And in the context of a machine learning model, I would argue that a model, depending on the input data and depending on the model architecture, could learn that embedding space just as easily as the original one. So a bit off topic, but getting back to the original point, right? What you really want to look at for embeddings primarily is the distance between them. And when it comes to distance, look at LT or we look at cosine distance, the actual individual elements of the vectors themselves don't really matter too much. The second thing, that I was talking about earlier, vector arithmetic, works kind of like this, right? So, and I'm trying to explain it as best I can without a whiteboard, but vector arithmetic works like, if I have an image of a sailboat, and let's say the sailboat is white, I take that image, I run that through an ML model, and I get a vector out of it. And then I have, let's say, text that using some multimodal model can be embedded into the same space. Let's say I have the text blue, right? The word blue. So if I were to take the embedding that corresponds to the image of the sailboat and take the embedding that corresponds to the word blue and I add them together, right? I add those two vectors together and I search for its nearest neighbor. Let's say I've indexed 1,000,000,000 images in Milvus and I search for their nearest neighbor. We would actually most likely find a picture of a blue sailboat, an image of a blue sailboat, right? Or if we were searching for text, we might have the text blue sailboat, right? And these types of sort of vector arithmetic applications, I think, are very, very exciting as well. We're definitely more focused early on the first chunk that I mentioned, the first half that I mentioned. So doing just nearest neighbor search. But the vector arithmetic, I think, is very, very that's really quite an untapped area as well. And I think a big area that Milvus will be looking into in the future. There's quite a bit of different applications when it comes to deduplication. And, there's many different ways to do it, right? This sort of ties in with what I was talking about in terms of what these embeddings mean and what these vectors mean, and that sometimes when you want to do deduplication, some of our users will actually take entire videos and try to do the matching there. In that case, if you have a very long video and very, very short segment that you want to dedupe out of it, it might not work as well. And then there's another subset where, let's say we have an hour-long audio snippet, and we'll divide those into very small chunks, maybe 10-second chunks, and we'll index all of those chunks inside of Milvus. That type of deduplication, because we do full vector deduplication, full embedding deduplication, is much more robust. It's a little bit more stronger. So when we look at an embedding, yes, we are taking this piece of unstructured data and turning it into this high-dimensional vector, but at the same time, we generally don't look at subsets of the vector. We don't look at individual columns or individual elements of that vector. It's more taking the input piece of unstructured data as a whole and turning that into an embedding.
One of the other things that I'm very curious about in this vector embedding space is the potential for implicit collisions in the ways that the vectors are represented, where you have a machine learning model or you have some custom algorithm, like you were mentioning in the case of the Android APKs, that will generate a particular vector representation of the information that you're trying to work with. But if you have two different machine learning models, one of them is being trained on audio data, the other one is being trained on images or LiDAR or biological sequences, what are the potential risks of accidentally ending up in a similar vector space with these completely disparate data types, where if you try to do a similarity search on, a genetic sequence, you end up finding the audio for a hit pop song by accident?
That's a great question. And I think when we talk about, you're sort of touching on the idea of multimodal learning, the idea that we have different modes of unstructured data. We have, I mentioned images, video, audio, text a little bit earlier in this podcast, but we also have other pieces of unstructured data as well. You were talking about, let's say, a genetic sequence. We have protein structures, graphs, maps, and, pop songs as well. These are all pieces of unstructured data. But I think once you really get down into the nitty gritty, if you have a model that's trained on, a lot of that is really up to the application developer to make sure that they don't fall into the pit hole of, accidentally taking protein structure and searching across a song database, right? One thing that I do want to touch on, I think I have mentioned this before as well, is the idea that we are going to see way more multimodal learning sort of methodologies in the future. I think a common one that you see already is images and text. There's really, really powerful ones out there that are trained over tons of data, probably, billions of examples, like Clip, for example, from OpenAI. And when you have these embeddings that are in the same space, you can do sort of like the vector arithmetic and other cool things that I was talking about a little bit earlier as well. The reason why I envision a vector database to be such a huge part of pretty much all applications in the future, or all applications that have unstructured data in the future, is because I think we're moving in ML, we're sort of moving into a direction where we want to embed everything. And not just embed everything, but also embed everything into the same space. So it's foreseeable one day that I could embed text and protein structures into the same space. And I could be able to search over protein structures just by saying, what is the kind of structure that I'm looking for, right? Giving it a textual query, turning that into an embedding, and then searching for relevant protein structures. It's also foreseeable that I could, given like a 3D molecular structure, I could find a pop song that maybe a pop song from a biomedical PhD that, they're singing about this protein structure, or they're singing about this molecular structure in one way, shape, or form. I think that's definitely foreseeable, right? I think the idea that embeddings are going to be a very, very core part of a lot of these future applications. I think the reason is because these embeddings are becoming so powerful from a semantic perspective. They're becoming, very, very much as a Swiss Army knife for different pieces of unstructured data and for correlating different pieces of unstructured data together. So, great question there.
It's time to make sense of today's data tooling ecosystem. Go to dataengineeringpodcast.com/rudder to get a guide that will help you build a practical data stack for every phase of your company's journey to data maturity. The guide includes architectures and tactical advice to help you progress through 4 stages: starter, growth, machine learning, and real time. Go to dataengineeringpodcast.com/rudder today to drop the modern data stack and use a practical data engineering framework. And now, digging into Milvus itself, can you talk to the architecture and implementation of the database engine and some of the core system requirements that have factored into the high-level design decisions about how to build this system?
For Milvus, and this ties into our Zillow's cloud platform as well, which is currently in early access. For Milvus, this sort of ties into the history of Milvus. Milvus 1 was, I think, very much a single instance. If you wanted to scale up, you needed to increase the number of cores that you had, or you need to, add more GPUs, you need to add more RAM. It was very much a single instance solution. And Milvus 2.0, Milvus 2.0 is entirely cloud native. It's production ready. It has a lot of database features that you would want to see in a distributed database these days, let's say like Cockroach or like Snowflake. It has failover, replication, full-fledged features that you want to see to put a database, any type of database, into production, right? Moving from Milvus 1 to Milvus 2 was actually really a huge challenge for us, because the only piece of the architecture that remained constant was actually the sort of compute engine that we call Nowhere. That's a Marvel movie reference. It was a big challenge for us moving from this single instance, thinking, okay, maybe we can take the data and have a store on that instance and do queries, indexing, searches, and storage all on that single machine, to a massive cloud native, cloud focused solution. And diving a little bit more into the architecture of Milvus 2, I'm going to focus on Milvus 2.x here. We've tried to separate out storage from compute, indexing from compute. We have multiple sort of different types of workers. We have data nodes, index nodes, and query nodes. These are all independently horizontally scalable from each other. A big thing, a very, very unique thing I think that we've done that I have yet to see any other vector database, either open source or closed source, do, is that we've separated a lot of these planes. We've separated a lot of the planes. We've separated compute from the storage. We've separated coordinators from the sort of workers. And it's also very much a streaming-based service as well. So we use Kafka or Pulsar as a part of the overall Milvus architecture. And what this has allowed us to do, it has given us the ability to, let's say, instead of provisioning a machine for our users, let's say our user, they want to use a vector database. They come to Zilla's cloud and they're like, hey, I have this application that needs a vector database. I want to be able to do something very quickly. Instead of provisioning a machine for them, what we now can do is we provision this solution for them. They have the option to purchase these compute units, right? And these units will serve as sort of currency for them to be able to do all sorts of different types of computation within Milvus. If they have, let's say, data and they just want to be able to store it, they don't want to do any compute over it just for the time being. Let's say they're it's still in a development phase or in an inactive state. They don't have to use any of those CUs, any of those compute units. And I think you see a lot of these sort of like data lakehouse models from Snowflake, Databricks that have done really, really well in this perspective. And we have tried to really replicate that for vector data as well. That saves a lot of effort in terms of application development for the user, but it also saves money as well. And for us, though, I think for us as a part of the Milvus community and on the Zilla's team as well, it definitely has been, the switch from Milvus 1 to Milvus 2 has absolutely been very, very difficult. And I want to say we've spent over a year and a half, 2 years just doing this switch alone, just so that we can have an architecture that is, yes, it's horizontally scalable. It's very, very flexible in that perspective, but also an architecture that is something users will be willing to put into production. It has all of these features, failover replication, across many different colos.
As far as the scalability aspects, I'm curious what the storage layer looks like and some of the challenges that you've run into of being able to figure out how do I shard or partition the different vectors in a particular collection that I'm trying to store so that I can optimize for speed of access and analysis to be able to provide this very quick interaction of being able to say, here's my input vector, give me the nearest neighbor so that I can determine what is the actual resulting out. I'm trying to doing the reverse image search, find me the closest image, and doing that in a time span that is interactive and conducive to an end user application.
This ties into the whole idea of a vector index, and great question as well. Absolutely keep these coming. This ties in the idea of a vector index as well, where in any database, you want to have indexes to help you do these queries very quickly. I think in like for maybe indexes based off of B trees or so on and so forth. But in doing these searches quickly, we want to be able to build these indexes in a very efficient manner. And for what we do, not just for Milvus, but for any vector database as well, for variety of different vector search or vector database solutions that you see out there, is that there's always an indexing component. There's always an index building component. And there are many different types of indexes that you can choose from. The most common one, I believe, is probably HNSW, which is a graph-based index. But Milvus, I think, is fairly unique in that our sort of core engine allows you to select from one of many different types of indexes. So HNSW, of course, is one of them, but we also provide another index, I think, originated from Eric Byrne at Spotify, when he was at Spotify, called Annoy, Approximate Nearest Neighbors, oh yeah. There are, we provide indexes based off of product quantization and just these flat indexes as well. So if you have, let's say, a very, very small database and you don't want to build an index specifically for that purpose, you want to search through all of vectors every time you do a query, that's absolutely okay as well. So these indexes, I'm not going to go into the details of how all of these indexes work, but these indexes play a key role in allowing us to search across massive quantities of unstructured data, massive amounts of embeddings at a very, very fast rate. So we always try to keep our query latencies within 5 to 10 milliseconds. And I think that's sort of the first answer to this. And I think the second part to this question is we have multiple functions within the vector database. There's indexing, querying, data, so on and so forth. There's a coordinator. Each of these functions can actually scale as you need them to. So, for example, if I have an application that's actually writing or doing updates, inserts, deletes a lot to my vector database, but probably not that many queries, I'm using it more as a storage engine, I can perhaps scale out the data nodes, I can scale out the indexing nodes as I see fit, right? On the other hand, if I have an application where the data is mostly static, or entirely static. I've seen a lot of those use cases as well, where the user will simply upload a lot of vector data to our vector database, leave it there for, let's say, however long. They'll be doing a lot of queries across it. We can scale out our query cluster in accordance with that particular use case as well to be able to utilize the indexes that we've already built and to be able to effectively, without boot up the right types of machines, that gives us the most amount of, I'm trying to search for the right word here, that gives us the most amount of efficiency and performance when we want to do those queries there. So I hope that more or less answers your question, Tobias, where there's the component of the index, but there's also the how we use that index internally within the Milvus architecture. Definitely would be a little bit easier if I had a whiteboard talking about all this, but yeah, I hope that's mostly clear there.
It's definitely a challenging aspect of running a podcast on these types of topics is when you start to get into the nitty gritty, you have to try and figure out how to build the appropriate word pictures without just completely turning everybody around.
I'm trying to correlate. I have this like a diagram sort of in my mind, and I'm trying to figure out which pieces of that diagram is relevant for the topic at hand. But please go ahead.
As you were talking about the architecture allowing for tuning these different aspects of how the database is being used and being able to support various workloads, where you might have a heavy write capacity and a light read capacity or vice versa, that also brings up the question of the CAP theorem and where it sits in the CP versus AP continuum and some of the ways that you think about that, particularly as you're tuning it in these different directions for high throughput or expanded storage capacity, high write, high read volumes, things like that.
I am actually really, really glad that you asked that question, because here at Zilliz, we have what we like to call the new CAP theorem. So for us, the C is sort of cost effectiveness or cost efficiency, right? And I'll talk about all the C, the A, and the P as a little bit later, but the A is accuracy and the P is performance. This is what we call the new CAP theorem for vector databases. There's probably going to be a blog post coming on that very soon, but I'll go over it very quickly here. The idea is, let's say I'm a very, very large company. I have a lot of data. I want to be able to search for the data very, very quickly, but I also want to do it very, very accurately. By accurately, what we mean is I want to search for the actual nearest. If I search for the top 10 nearest neighbors, I want to be able to get the actual top 10, let's say 99% of the time or 99.9% of the time. This sort of fits in with, I didn't go too much into detail of this, but this sort of fits in what we were just talking about vector indexes, where you have this index, but it is inherently probabilistic, right? It's not deterministic like you would see for, let's say, a relational database or a database for a semi-structured data object database. The idea being that when I do this vector search, it is approximate nearest neighbor search. It is ANN. The index allows me to search for the approximate nearest neighbors to a particular query vector or a query embedding. There are some different parameters that I can tune to give me a much higher probability of getting the actual nearest neighbors. If I search for the top 10, perhaps I only get the top 10, let's say 90% of the time. There are some knobs that I can tune to give me maybe 99% or 99.9%. So that's where the accuracy perspective of the CAP theorem comes in. The CAP theorem for vector databases. There's accuracy. I'm a very large company and I want to be able to very accurately and very quickly search for my top nearest neighbors, let's say my top 10 or top 100. In that case, I could throw a lot of machines at it. I could throw a lot of compute resources at it, say like hundreds of machines. And I could really get my results very quickly with very, very low latency, very high throughput. And at the same time, I would get very, very accurate results. So I would pretty much always get the top 10 or the top 100 or the exact top N that I'm looking for. But you're throwing so many compute resources at it, it's not very cost effective, right? It's going to have very high cost in terms of CPU, GPU. If you're running accelerators like an FPGA accelerator, it'll have high cost in terms of these accelerators as well. In line with the CAP theorem for more traditional databases, it's really a choose 2 out of 3, right? Now, if I have an application where, let's say, I am less concerned about accuracy, I don't need as heavy of an index, I can actually do the querying much faster, but then I lose a lot of the potential top N accuracy. So let's say I can do a query much quicker with fewer resources, but perhaps I only get, in the top 10 results that I get, maybe only 7 or 8 of them are in the real, quote unquote, the actual top 10 results. So in that case, I've traded off accuracy for cost effectiveness, right? And there's also other examples where you may want the C and the A rather than the P. Maybe I can withstand these 1 second or 2 second latencies, very, very low throughput, but I want to use very few machines. And at the same time, I want very, very accurate results. We've seen a lot of those applications come in when it comes to 3D molecular search as well. So yeah, this is sort of like it's sort of like a sneak peek of what we like to call the new CAP theorem for vector databases. I sort of went off on a tangent there, but I can never resist the opportunity to talk about this with other folks.
Absolutely.
So, hope that sort of makes sense.
No, it definitely does. And so from a practical perspective, for people who are interested in using Milvus, they are either using machine learning models to generate these embeddings, or they have their own specific algorithms for being able to build these vector representations. What is involved in the process of actually getting it set up and integrating it into an application and building on top of it? And in particular, thinking about some of the data modeling aspects of how do I assign appropriate metadata, what are some of the organizational capabilities, being able to understand what the sort of concurrency capabilities are, things like that.
Milvus, I think today is easier than ever to get set up with. Milvus inherently, we have a distributed architecture. So, it uses Kubernetes as sort of like the execution engine there. We have Helm charts that you can use just right off, just straight from the Milvus.io website that you can use to deploy a Milvus cluster into on-prem. And really the whole idea there is that we try our best to abstract away as much of the vector database maintenance as possible. Now, if you do choose to do on-prem, you obviously still have to maintain the compute resources, the compute resources on your own end. We also, as I mentioned earlier, have a cloud version that currently, as of July 2022 is in early access, sort of like a closed beta type thing. And, we will open it up to other users, I want to say in about a month or two as well. So definitely keep on the lookout for that. But when it comes to actually getting up and running with a Milvus deployment, I think it is absolutely easier than ever, especially as it comes to Milvus 2.x, our cloud native version of Milvus, where you can, if you want to play around with it just locally on your laptop computer, maybe you're a data scientist, you want to index a very small number of embeddings, let's say only 5 million or 10 million embeddings, you can absolutely do so. You can do it with a simple, if you're running Linux, you can use apt-yum, do a standalone version of Milvus. And then what I think is very, very unique is that we can later on, if you do decide to put that data into production, you can sort of take that, because we use MinIO as the underlying object storage across all of our platforms, you can take that and essentially put it into production, quote unquote, very, very easily, right? You can put it into a cloud native, you can put it into cluster mode very, very easily. And, we're working towards being able to do the same for our Zilla's cloud platform as well. where if you have an internal on-prem Milvus instance of Milvus, across your cluster, you can do the migration to cloud as well. So you have all these vectors that you're storing locally in an internal cluster. We give the option to do that. We will have the option of having all of that data in cloud in a managed service as well. So there's different levels, I think, that organizations or companies, research groups are comfortable with. And we try to make, for each of those levels of comfort, I guess, so to speak, we try to have a solution. We try to have something for all of those users.
When it comes to actually building an application on top of Milvus, you have the ability to do these nearest neighbor searches on these vectors. And for the case of, for instance, the reverse image search, I'm wondering if you can talk to some of the ways that you go from, I have this input vector, I determine this is the nearest neighbor to that, and then mapping that nearest neighbor vector back to the actual source object to be able to return the image that you are looking for, and some of the ways that you think about the application architectures where you're using Milvus for these fast searches, but then mapping that into the broader application architecture and the ecosystem around it.
Specifically when it comes to the case of reverse image search, we actually leave the non-vector data management more so up to the user. And I think that we do that for multiple reasons, right? The first is to give in the application layer sort of like a level of flexibility, some certain degree of flexibility for the application developer or for the engineer who's working with a vector database. The second reason is because it also simplifies things for us, right? So typically, if I were building, let's say, a reverse image search system, I think it's one of the very common ones, one of the very common applications for a vector database. What you want to do is we work primarily just with the vectors themselves. So if you have a vector that corresponds to an image, you can insert that into Milvus. Milvus will do all of the indexing, the flushing, the sort of vector data management in the background. And Milvus will actually return sort of like an object ID. So it's very analogous to the _ID field in MongoDB, right? Or essentially something that corresponds, something that you can use to map the embedding back to your original object. When we return that object ID, or not an object ID, but when we return that ID more generally, it is really up to the user in the application level to figure out what that ID, which piece of unstructured data that ID maps to. And you see this already ties in with what we were talking about earlier, what we were chatting about, how a vector database is not really meant to replace these relational databases or replace these key value stores. There's always the use case, let's say I have an S3 path that corresponds to an image, or I have a file on my local disk that corresponds to an image that I want to index in my reverse image search solution. I still need some other external way of mapping, let's say, that URL or that path on my local drive to that particular object ID. But all of the vector data management, all of the unstructured data management, so to speak, that is left entirely. You can leave that entirely to Milvus. We will figure out a way to store that vector. We'll figure out when to index that vector into one of the ANN algorithms that I was talking about earlier. And we'll figure out how, when you have a new vector that you want to query across the existing, that you want to use to query across the existing database, we'll figure out how that query can be done most efficiently. So that's just specifically in the example, if you want to build a reverse image search system. But I think that also ties in with many of the other systems many of the other applications that we were talking about earlier as well. So if you were to do video deduplication, you would have these video snippets, you would index them, and you would do nearest neighbor search. If the distance between a particular input and its nearest neighbor was close enough, you would say, okay, this is a duplicate of the input. And again, it goes through a very similar flow there, where you have the data, you get the input video snippets, and you want to figure out which of the ones in my database are sort of related.
Data teams are increasingly under pressure to deliver. According to a recent survey by Ascend.io, 95% reported being at or over capacity, with 72% of data experts reporting demands on their team going up faster than they can hire. It's no surprise they are increasingly turning to automation. In fact, while only 3.5% report having current investments in automation, 85% of data teams plan on investing in automation in the next 12 months. That's where our friends at Ascend.io come in. The Ascend Data Automation Cloud provides a unified platform for data ingestion, transformation, orchestration, and observability. Ascend users love its declarative pipelines, powerful SDK, elegant UI, and extensible plugin architecture, as well as its support for Python, SQL, Scala, and Java. Ascend automates workloads on Snowflake, Databricks, BigQuery, and open source Spark, and can be deployed in AWS, Azure, or GCP. Go to dataengineeringpodcast.com/ascend and sign up for a free trial. If you're a Data Engineering Podcast listener, you get credits worth $5,000 when you become a customer. In terms of your work on building Milvus and using it at Zilliz and working with your customers and the community members who are building things on top of it, what are some of the most interesting or innovative or unexpected ways that you've seen Milvus used?
I'll go over three, and I think I've touched upon this a little bit earlier as well. I'll go over three of my favorite applications. The first is AI drug discovery, as we like to call it, where you have a pharmaceutical application, or you have a variety of these different proteins, a variety of these different molecular structures. And again, I was not a biology major in college, so probably not the best person to ask about some of the science or some of the biology behind this. But you take these molecular structures and let's say I have a particular drug that does something, that accomplishes something, perhaps tackles a particular symptom, or it has some effect in the body. They also want to be able to replicate using, let's say, some other type of molecular structure, right? That's one of the interesting applications that I've seen with Milvus there, where you can actually discover new drugs based on molecular structure of existing drugs that tackle a particular problem. I did mention where there was stuff that we did with Trend Micro when it comes to security, when it comes to antivirus, and when it comes to sort of malware. There's also sort of packet inspection, a lot of other things that can be done there as well. I did touch upon this earlier. There was also something that we did with Cleveland Museum of Art. That one is probably, I think, even though it is a very, very common use case, it's reverse image search, I think it's probably still my favorite. I'd like to talk about this one quite a bit because Cleveland Museum of Art does not have a very, very large engineering presence, but they were still able to create something very, very quickly within a week, this reverse image search system. This particular solution, I believe, is called AI Art Lens. I believe that's the name. I do encourage everybody to go look it up. When folks talk about we are democratizing this or democratizing that, it can end up being a catchphrase for just taking whatever it is that you're building and saying, we are making this available to everybody. But when really push comes to shove, I think being able to take something that traditionally has been very, very difficult to implement, like reverse image search, if you look at maybe 5-10 years ago, it was pretty involved to build a reverse image search system. And on top of that, it was probably, the performance might not have been that great either, especially, I want to say, pre-ConvNets, before transformers and before convolutional networks. But today, I think when you see a combination of the plethora of models that are out there, great models as well for computer vision, for NLP, for audio, for video, you see vector databases, you see a vector database like Milvus, combining these two and being able to do all of these very, very unique search solutions and these very unique recommendation systems. I think that's really what is amazing to me about some of the infrastructure that we're building, in conjunction with the greater Milvus community, right? That's really why I choose to focus on, we have like a number of sort of enterprise users that have much bigger deployments of Milvus. So like Compass, Shutterstock, I believe they use Milvus internally. Those are two other examples. We have a great number of enterprise users that deploy and use Milvus internally, but I always like to focus on the smaller deployments. I always like to focus on the ones that maybe required like a one person week or maybe even one person day to accomplish, because those to me that is why I love the Milvus ecosystem so much. That's what really brought me to Zilliz. That's what really keeps me, engaged with the Milvus community and with a lot of the folks that I speak to, is the capability of, for even these very, very tiny teams to do something incredible that they wouldn't have been able to, let's say, 5 or 10 years ago.
In your experience of working on Milvus and building around it Zilliz and working with the community, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
as an open source community, we always get a lot of folks who come and ask questions about Milvus, and they say, oh, how do I tune this particular parameter to get better performance out of my database? And that's great and all, but I think what we've really seen in just the past year, I want to say from like April, May, or June, that kind of time frame, is an uptick in the number of folks who are actually engaged in terms of, there's some work that I want to do, there's some particular development that I want to do, I want to help contribute to the Milvus community as well. And when it comes to open source, when it comes to community engagement, I really do believe that the best open source communities have folks who want to be engaged with the open source project, with the project itself, not only as a user, but also as a contributor. We have definitely seen a massive uptick within the Milvus community, and even in the past year. I think part of it is due to we have these other projects that are a part of the vector database ecosystem as well. I'll mention them very, very briefly here. We have Tohi, which I actually sort of co-created that open source project with some of the other folks at Zilliz. And Tohi is all about doing the upstream embedding generation. It's much closer to machine learning. It's much closer to Python, a bit closer to data science as well. I think through, all the people that we've brought on with Tohi, they've been able to take a look at Milvus and say, well, this is really awesome. And by combining Tohi with Milvus, maybe what took me 3 months, 10 years ago, what took me 3 weeks, maybe 3 years ago, I can do in 3 days today using these two open source projects. We also have these visualization tools as well as these management interfaces called Atu and Feder respectively. Obviously, I encourage everybody to go take a look at those on Zilliz.com. And these, by reaching out to a lot of the folks, in data science, in, front-end engineering, in even back-end engineering, folks who might not originally know about Milvus, by having this broader vector database ecosystem, I feel like we've been able to really reach out to many, many more people than we would have been able to if we just had Milvus, right? If we just had the vector database component itself. And seeing that kind of growth in the past year, not just for Milvus, but also for these other projects that I talked about, I think that has been, one of the shining points, in my time here and being a part of the community as well.
As you continue to build and iterate on the Milvus project and build your cloud offering at Zilliz on top of it, what are some of the things you have planned for the near to medium term, or any particular aspects of it that you're excited to dig into?
I won't go too much into Zilliz Cloud. Obviously, what we're looking to do is take what we have done in the open source community, take Milvus, make that accessible to a lot more people who want to manage service. Zilliz Cloud, we will continue to add features, add functionality to that. We're going to onboard, as I mentioned, the entire vector database ecosystem. We're going to onboard Tohi to that. I want to say our goal is around June or July of next year to be able to have this embedding generation platform on Zilliz Cloud as well. When it comes to Milvus itself, we are going to continue to improve Milvus not only in terms of speed, but also in terms of accessibility. We are adding hybrid search, so the ability to search across both metadata as well as the embedding itself. There's going to be GPU support and perhaps even further down the road, some accelerator support as well, FPGAs, TPUs, NPUs. My background is actually, I was an electrical engineering major in college. So these accelerators are very near and dear to my heart. Where, in addition to hybrid search, I do want to say that, probably we're going to be looking at some point at some more advanced functionality as well. There's quite a few things that we want to do that we really haven't gotten to yet that we'll try to be pushing out with Milvus 2.2, 2.3, and Milvus and beyond, right? Milvus 3.0, 4.0, so on and so forth. All these features we obviously plan to have on our cloud platform as well, on Zilliz Cloud, to really make that accessible to as many people and as many organizations as we can.
Are there any other aspects of the Milvus project or the overall capabilities of vector databases that we didn't discuss yet that you'd like to cover before we close out the show?
I do want to speak a little bit more about the broader vector database ecosystem. I did touch upon this earlier. I want to introduce some of these other open source projects that we have in a little bit more detail. Tohi is meant to be this upstream embedding generation platform. We refer to it internally within Zilliz as the new ETL for unstructured data, where you see traditionally a lot of these ETL platforms have always been about doing data loading, doing this data transformation, and perhaps creating data as an input into machine learning models. But as machine learning and as these embedding generation methods become more and more sort of production ready, more and more solid, you see them be a part of the ETL pipeline as well. And that's really what Tohi aims to do there. We have Atu, which is essentially a management platform for your vector data. It is a management front end where you can actually go and very, very easily, let's say, take a look at some of the internal workings of Milvus, and Fetter, which ties into that as well. It is an ANN search index visualization tool. I think anybody who goes and take a look at that will be like, well, this is really, really awesome. Where you can actually visualize a lot of these ANN algorithms in JavaScript. So you can see how HNSW, how it works in terms of the different layers, in terms of algorithmically, okay, perhaps this is how this approximate nearest neighbor search is being done with a single query vector. So that's sort of a bit more of an introduction to the broader vector database ecosystem that we have been developing at Zilliz in conjunction with Milvus. Obviously, Milvus still forms the core of our engineering efforts in conjunction with the broader Milvus community. But I definitely did want to bring these up, and I think these will continue to form a core part of what Zilliz is trying to do and really trying to build these tools and build the ecosystem around Milvus as well.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I think coming from a machine learning perspective, I think the intersection of ML and data, and it really goes both ways. So sort of DB for ML and ML for DBs. I think there's a lot of work that can be done there. There's a lot of work that can be done in both of these areas. These are two very unique areas, mind you. Vector databases and other platforms like feature stores, so on and so forth, these are very much in the DB for AI ML area. And then you see a lot of work being done, I want to say primarily in academia these days, where there is ML or AI for DBs as well. Maybe to, let's say, speed up these. And there might be sort of more work that's being done out there, but maybe, if I have a particular query and I can use ML to, let's say, figure out maybe how long that query is going to take to execute. This is just one particular example, right? So the intersection of data and machine learning and AI, I think there's really quite a bit of work that can be done there, both in terms of infrastructure as well as in terms of algorithms.
All right. Well, thank you very much for taking the time today to join me and share the work that you've been doing on Milvus and at Zilliz. It's definitely a very interesting project and interesting problem domain. It's great to see an open source offering in the vector database space. So I appreciate all of the time and energy that you and the other members of the Milvus team are putting into that, and I hope you enjoy the rest of your day.
Thank you, Tobias.
Thank you for listening. Don't forget to check out our other shows, podcast.init, which covers the Python language, its community, and the innovative ways it is being used, and the Machine Learning Podcast, which helps you go from idea to production with machine learning. Visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.